Welcome once again to a tutorial on the BJT, and in this tutorial video we're basically going to discuss about the operational modes of a BJT device. Okay, so as far as we've discussed on this particular device, it's I've just said that BJT is obviously optimally suited for operation when you have to forward bias the emitter junction and reverse bias the collector junction. But there's of course three basic modes in which the BJT can be operated also. So first up, we've got the common base mode of operation of that of a BJT. Okay, now this particular mode, we always need to ground the base terminal of the device. So this particular mode of operation of a BJT is also referred to as the grounded base configuration, or rather the grounded base mode of BJT operation. Okay, next we got the common emitter mode, okay, also referred to as the CE mode. I like to also mention the fact that the common base mode is also referred to in short as the CB mode. Alright, so now as in the case of the common base mode of operation of a BJT device, the common emitter mode is also referred to as the grounded, that's right, grounded emitter configuration, or rather the grounded emitter mode of operation of this particular device. Now similarly, as you've seen in the case 1 over here, in case of the CE mode of operation, the emitter terminal is also grounded. Okay, and finally we have the common collector mode, or rather referred to as the CC mode in short, and like the previous two, it's also called the grounded collector mode, as the common collector, that's the collector terminal, which is of course common over here, must be grounded in order to achieve this mode of operation of the device. Okay, now that said, we'll just quickly move on into the the operational mode, which we're going to discuss in detail over here. That is, of course, you've guessed it right, that's the CB mode, or rather the common base mode of operation. That's exactly what we are going to discuss in detail over here. Okay, so before we go on to the details of this particular mode of operation, let's just bring the circuit diagrams for both the PNP and the NPN transistors as well. Okay, so there you go. Now we have the diagrams for both the PNP type BJT on the left and the NPN type BJT on the right, whenever they are just configured in the common base, or rather the CB mode of operation. Okay, so now in order to get into the details, you can also see that the bias voltages are given in an given in a manner so that the emitter junction in both the cases is forward biased, while the collector junctions are reverse biased in both the diagrams. Okay, so now as I was saying that if we need to study this particular mode of the BJT operation in detail, we need to delve into the input and the output characteristics as well. So let me just tell you before we go on further with this topic, that if you take a look at the PNP type BJT diagram over here, you'll see that to the left of the base terminal, I'm just talking about this part of the circuit where we have the emitter junction, the emitter terminal, and the V1 voltage. Okay, that part of the circuit over here forms a loop, and that's known as the input loop. So I'm just going to write down over here. So there you go, that's the input loop of this particular BJT circuit in case of the PNP type BJT. And the other one that is formed with the collector terminal, the collector base junction, and the V2 voltage source over here, that's on the right, this part of the circuit that I'm talking about, is known as the output loop of this particular configuration. Okay, similarly in the case of the NPN type BJT, the input and the output loops are obviously in the same way as you've seen in case of the PNP type BJT configuration. Okay, so let's just go on to the details. So here we're basically going to discuss about the input characteristics first. So there you go. So we're going to discuss about the input characteristics. Now let me just tell you before I move on further that the input characteristics is it's basically a graph, or rather a curve, that you need to plot versus in which you just compare the emitter base forward bias voltage and the input emitter current. So here we're just gonna plot a graph between the emitter current versus that of the input, the emitter base bias voltages. So here if you just take a look at the diagrams over here again, then we can see that this part of the circuit over here is of course where we get the emitter base bias voltage in both the cases of the two types of BJT that we've seen over here. Okay, so now in order to study the input characteristics over here, we need to modify the previous diagrams a bit. Okay, so I'm just going to modify them right here. Okay, that's the modification you're going to need in both the case of the PNP and the NPN type BJTs. So you can see here at the input loops of both the types of BJTs that we have shown over here, we've connected an emitter, okay, at the emitter terminal in order to measure the amount of emitter current entering or leaving from the emitter terminal. Okay, and also we've connected a voltmeter VA across that of the emitter and the base terminals in order to measure the amount of emitter base bias voltage. Okay, so in the case of the PNP type of BJT, it's quite natural that the emitter current would just flow from the input source voltage V1 into that of the emitter terminal. So I'll just write down here. Okay, I'm just gonna write this one over here as IE. So this arrow mark over here represents the direction of the emitter current into that of the PNP type BJT. Well, in the case of the NPN type BJT, this direction would be just reversed. So here we have our emitter current in case of the NPN type of BJT device. Okay, so now looking at these figures, if we just study them, and here we're just going to keep the V2 voltage source fixed. So here we're going to keep V2 as a fixed voltage source. So we're just going to keep V2 at a particular voltage, okay, and we're just going to vary the voltages present in the we're just going to vary the voltage, bias voltages across the emitter and the base terminals. So we are going to keep V1 as a variable voltage source in both the cases. Okay, so we're just going to vary V1. Okay, so we're going to keep V1 variable. Okay, there you go. And also by varying the V1 voltage over here, the emitter current that's given by IE would also vary. So we're going to keep V1 and also IE variable so that we can plot the graph of IE versus VEB. Okay, so if we are just gonna if we're just gonna straight away plot the graph over here, then we're gonna get a graph that would look something like this. Okay, so that's what we should get over here. So you can see that the graphs of both the PNP and the NPN transistors input characteristics have been provided over here. Well, a closer examination of the curves show that they are strictly they represent, or rather they resemble, the characteristics of a diode, a forward biased p-n junction diode curve. Okay, and that's quite natural, is because in the circuits over here, since we're just basically forward biasing the emitter base junction, which is actually a p-n junction, so that we are getting the emitter base bias voltages in both the cases. So it's quite natural that since we are forward biasing this particular p-n junction present between that of the emitter and the base terminals in both the types of BJT, then we are supposed to get a characteristic that would resemble something like this. And here we are also measuring the emitter current in both the cases. So here it is, that's IE. That's the emitter current, and that's measured in milliamps in both the cases of the types of transistors. Okay, so you can see that all the voltages that have been taken over here, and also the currents, not the currents, sorry, the voltages that we have just taken here for the emitter base forward bias voltages that you can see over here, they have all been taken with respect to the ground terminal at which the base terminal is just connected. So for the PNP type of BJT, the forward bias emitter base voltages are all positive, while that in case of the NPN type transistor, we have the forward biased emitter base voltages all taken negative. And also the direction of currents in both the cases of the transistors differ. So if we just take the current direction for that of the PNP type of BJT to be positive, then we are supposed to take the current direction in the case of the NPN type BJT to be negative, since it's just directed in the opposite way. So that just gives us an idea about what sort of characteristic we should well expect for both of them. And well, let's just consider the fact that we had taken this as a condition where we kept the output voltage source, that's V2 over here, as fixed, as I've just written down over here. So now if you just keep or rather manage to keep V2 variable, then we're going to see a difference in the curves over here. So let's say that let's just say that we have kept we got this particular curve for, well, the collector base bias voltage of about, let's say, 0 volts. So whenever we did not apply any sort of collector base bias voltage. Okay, now let's just, well, make this one as a variable term. Okay, so I'll just rub it off and make it variable. Okay, that's better. So in that case, I'm just going to write it down over here, variable. So now if we would just care to put well, VCB equals to about, let's say 5 volts, then in that case, and also we have connected another voltmeter over here named by VB, okay, in both the cases, in order to measure the amount of reverse bias voltage now falling across the collector and the base junctions in both the types of BJTs. So in that case, we are supposed to obtain a graph that would look something like this. You can see that the yellow line over here represents the change in the characteristic curve whenever we put, let's say, VCB equals to about 5 volts. So whenever, in this case it'll be a -1. Okay, I'm just gonna write it down clearly. All right, that's better. So in the case with a PNP type of a BJT, the reverse bias collector base voltage is of course taken negative with respect to that of ground, while in the case of the NPN type of BJT, the reverse bias collector base voltage is taken positive with respect to that of ground, depending upon the voltage source terminals being connected and their polarities, of course. So over here you can see that, well, the curve has, well, shifted a little towards the left, which means that the current, well, rises much more sharply in this case as in the previous. And then if we just go on increasing VCB even more, then we're obviously supposed to get this pink curve that we're are seeing right now in both the case of the PNP and the NPN type transistor. So you can see that, well, keeping VCB equals to about, let's say, -8 volts over here in the case of the PNP type of BJT, while in the case of the NPN type BJT we just kept it as equals to 8 volts. So you can see that the curve, well, shifts even more towards the left on increasing the amount of reverse bias collector base voltage. And this particular effect is due to the early effect that we had previously discussed in our previous tutorial. So the early effect, what it basically does is that it decreases the base width under higher amounts of reverse bias voltages when we just apply them across the collector base junctions, in a way, in order to just enhance or rather increase the amount of concentration gradient in the base section itself, so that the more amount of emitter current just enters into the base readily with a very, very little change of the emitter base forward bias voltage. Okay, so now we just quickly move on to the output characteristics over here. Okay, so in this particular output characteristics, we have just modified our circuits a little bit, and we've eliminated the voltmeter that was known as VA, that is connected across the emitter base terminals in order to measure the emitter base forward bias voltage. Now we don't need to measure any of that over here, because here we're just trying to find out the variation of the collector current versus that of the collector base bias voltage. It's of course required to maintain the emitter base terminal at emitter base junctions over here at a forward bias voltage. So maintaining that at a particular, or rather at an optimum forward bias voltage, we can just, well, go on varying the output. We can go on maintain the or rather varying the collector base bias voltages in order to note the changes in the amount of collector current. So for that of the PNP type of the BJT, the direction of the collector current is of course, well, outwards. So there you go. And for that of the NPN type BJT, the direction of the collector currents is inwards. That's towards the device. Okay. So now if we would just, in that case, if we would just basically take the direction of collector current to be positive for that of the NPN type of BJT, then in the case of the PNP type of BJT, the direction of collector current would be reversed, so that we need to take it as a negative. Okay, so in that case, if we just keep on varying the collector base bias voltage, so I'm just going to write it down over here. So we're just going to do that by varying the voltage source V2. So we're going to keep V2 as variable. Okay, and then also that would just lead to the collector current IC to be variable as well. All right, and finally we're going to keep the input voltage, that's V1 over here, as a fixed voltage source. Okay, so for a fixed value of V1, and also where the emitter current would be fixed as well, so IE would be fixed over here. So under the fixed values of the V1 and the emitter current over here, we're going to note the changes that would of course take place, or rather the characteristics that would be generated due to the variation of the collector current and the collector base bias voltages. So we're going to get graphs that would look something like, okay, here you are. There are the graphs of the output characteristics of that of the both the PNP and the NPN type BJT devices. So you can see over here that the red line represents the variation of the collector current versus that of the collector base bias voltage. So you can see that as soon as we just go on increasing the collector base bias voltage, we can see that the collector current rises to a certain extent, and then it saturates to a particular value of the collector current. Okay, so now we can primarily see over here that the both the graphs, that's the output characteristics, are divided into three major regions. Okay, so we have this region below that I'm just shading in white. Okay, there you go. This particular region below, that's known as the cutoff region in both the graphs. Okay, I'm just going to name it over here. That's the cutoff region. Okay, now this cutoff region, of course, represents the case where the emitter current is absolutely zero, so that the amount of collector current would just be equal to the reverse saturation current present in the reverse bias collector base junction. That's known as the ICO. Okay, remember now? Okay, so now apart from this cutoff region over here, we also have the other region that exists between the zero collector base bias voltage and about a little bit of forward voltage existing, although it's nearly very close to zero, but a little bit of forward bias voltage existing across that of the collector base terminals. Okay, so this is the region that's known as the saturation region. I'm just going to write it down over here. So there you go. So the saturation region actually represents that particular region of the output characteristics curve where both the emitter base and the collector base terminals are basically forward biased. Okay, so now apart from the saturation region of this particular output curves, we also have the other region in the curve where the collector current becomes primarily immune to all changes that are produced by increasing the collector base bias, reverse bias voltage. Okay, so that particular region is just known as the active region of the output graph. Okay, and the BJTs are primarily operated in the active region of operation, so that no fluctuations occur in the bias voltages. Okay, so apart from that, if we just take a look back into these circuits over here, we've kept the input voltage, that's V1, as fixed. So if we just try and make the V1 variable and try and studying the the effect of variations in the values of the emitter current from affecting that of the output characteristics, then we're gonna notice something like this. All right, there you go. So let's just start from the beginning. So when we are just keeping the emitter current to about, let's say, 0 milliamps, that means we're just not applying any sort of forward bias voltages on the emitter base, in order to forward bias the emitter base junction, then this is what we have over here. The collector current is just primarily equal to the ICO, that's the reverse saturation current present in the reverse bias collector base junction. Okay, now if we just tend to Okay, now so IE increased to 10 milliamps by just forward biasing the emitter base junction, then we're going to get, well, a higher curve where we can see that the collector current is, well, strikingly equal to that of the emitter current over here as well. And if you just, well, increase the forward bias voltage on the emitter base terminals further, that whenever we just increase the value of IE to about, let's say, 20 milliamps or let's say 30 milliamps, the collector currents just become strikingly equal to that of the emitter current. So from these output characteristics, we just come to the conclusion that, well, the emitter current is approximately equals to that of the collector current for the common base configuration. So with that kept in mind, we just come to the end of this tutorial video, and so far that you've known about the common base mode, don't forget to watch our next videos where we just explain about the rest of the operating mode. So till then, it's just gonna be a short goodbye for now, and thanks for watching.